In this lecture video, we will continue our discussion of the atmosphere and how it controls weather. In this chapter, we'll take a look at air pressure and look at wind and discuss what wind is and the different types of winds that exist both on the surface of the earth as well as into the atmosphere. So, air pressure is key to understanding how we get different weather events that occur on Earth, as well as understanding where wind comes from and why wind blows in the direction that it does. So, air pressure is just the force or the pressure that's exerted by the weight of the air above us. So, as we're walking around on Earth, there is, a column of air above us, and that air is pushing down on us. And so the weight of air at sea level is 14 pounds per square inch, which is an amount that we call 1 atmosphere. Now, as we increase altitude, air pressure decreases because that column of air is not as big, it's not as tall. So since that column of air isn't as tall, the higher we go, the less air pressure there is. In meteorology, the unit of measurement used to define air pressure is the millibar, but we also use inches or millimeters of mercury. So we're going to watch a smart figure video that goes over a little bit more detail about air pressure.
Hello, this is Callan Bentley. Welcome back for another smart figure. This video is about air pressure, so after watching it you'll have a better sense of why we have air pressure and how we measure it and what the range of different air pressures is typically. Consider the atmosphere. You're standing on the surface of the Earth and you have air above you. If you take a slice through that overlying air and looked at it in detail, you would find that it's made out of lots of little particles. Some of them are in the gas phase, some are solids that are suspended in the air, and some are little liquid droplets. Regardless, all those little particles are matter, and so they have mass, and they weigh down on the objects that are beneath them. So if you think about that pressure, think about a column of air, and basically that little column is going to measure 1 inch on each side. So we've got an area of 1 square inch, and then think about all the air above that square inch. Basically, there's going to be enough matter there that it exerts 14.7 pounds of pressure downward. And another way of expressing that in metric would be 1 kilogram per square centimeter. So there is significant pressure that's exerted downward by the air above you. It might not feel like you have 14.7 pounds on every square inch of your head, but that is indeed the case. We can measure air pressure a couple different ways. One of them is shown here. This is called a Mercury Barometer, and basically you've got this open container of mercury here. The weight of the air is pushing down on that mercury, and it forces some of it to go up into this little tube. At the top of the tube is a vacuum, so that vacuum is going to be exerting a little bit of outward pressure on the mercury inside the tube. But if the air pressure is greater than that outward pressure, then that mercury is going to move up to a higher and higher level. So this is what they're talking about when you'll hear, like on the news, they talk about so many inches of mercury of air pressure. So that'd be like almost 30 inches of mercury in that tube. We can also express air pressure in millibars, shown here on the right side of this column. And the typical average air pressure at sea level is 1,013.25 millibars, and that's equivalent to about 29.92 inches of mercury. There are air pressures that are higher than average, and there are air pressures that are lower than average. Let's take a look at some of the highest air pressures here. A strong high pressure system, an anti-cyclone that we'll be talking about in a future smart figure in the next chapter, would be like around 1,040 millibars. That's around 30.7 inches of mercury. The highest recorded sea level pressure in the United States was in Montana, and you can see that it was around 1,064 millibars. And the highest recorded sea level pressure anywhere on Earth was in Siberia, and you can see that that was around 1,084 millibars. There are lower than average pressures too, a strong low pressure system, which is a mid-latitude cyclone. This is going to be somewhere on the order of 980 millibars or 28.9 inches of mercury. And then there are the really low pressure system features such as Hurricane Katrina. That's a famous one. That was around 902 millibars at its lowest pressure, so in other words, the strongest winds. Hurricane Wilma and Typhoon Tip are record breakers that are even lower pressure than that. You can see Typhoon Tip was around 870 millibars, 25.7 inches of mercury. So how does that relate to this picture? Well, here we have a typical low pressure system, a tropical cyclone, where we have low pressure in the middle. So that low pressure area there is basically almost like a vacuum sucking the air in from the surrounding higher pressure areas. So you could think of high pressure being over here in the northwest, and also some high pressure here in the northeast, some high pressure down here in the southeast, and some more high pressure over here in the southwest. So basically what that air wants to do is it wants to go from high pressure towards low pressure, but instead of taking on that straight line path like it would on a non-rotating planet, the winds on Earth, because Earth is rotating, are bent towards the right in the northern hemisphere and towards the left in the southern hemisphere. So you end up basically with this overall spiral pattern to the wind flow direction. Thanks very much for your attention. This has been another Smart Figure.
So in the video, you learned a little bit more about air pressure and how we measure air pressure. And he mentioned the Mercury Barometer, which is an exact measurement, or allows us to get an exact measurement of air pressure. However, it's not very portable. And so we have the development of what's called the Anaerobic Barometer. Anaerobic means without liquid. So this is a much more portable barometer. There's a vacuum chamber that's kind of underneath this, is kind of showing you a side view here. It's partially empty. So it's got a little bit of air in it, but it's not full of air. This chamber is going to be sensitive to changes in the air pressure. And so it's going to change shape, compressing when the pressure increases, and then expanding when the pressure decreases. And so it's set up on this little series of levers. And as the air pressure changes, this pointer, this black line here, will move. And then this kind of gold one here, you can set that to where the measurement is, and then, go away for a few hours and come back, and then that'll tell you if there's been a change in pressure. Because the change in air pressure is much more important than just knowing what the exact air pressure is at a given point in time. Falling pressure, as you learned from the video, is more associated with storms, and a higher air pressure or rising air pressure indicates typically that conditions are going to be clearing and we're in for good weather. And that's why, you've got over here the higher pressure, fair and dry, and over here on the left, the lower pressures, stormy and rainy. The other thing about an anaerobic barometer is that it can be hooked up to a recording paper. So it can be hooked up and the changes allowed to be graphed over a given period of time. So wind. Well, wind is the horizontal movement of air. And air is going to move from an area of high pressure to an area of low pressure because it follows that pressure gradient. So wind is air that's traveling in a direction toward areas of low pressure following the gradient. Wind is going to be nature's attempt to balance inequalities in air pressure. So as we area of high pressure to an area of low pressure, the goal is to even those out, to get back to where we have equal air pressure. The changes in air pressure is due to unequal heating of the earth. We talked about that a couple of chapters ago. How, darker surfaces over land absorb more heat than lighter colored surfaces or the ocean. So this unequal solar heating is what accounts for these pressure differences. So solar radiation then is going to be the energy source for most types of wind. So wind is controlled by a combination of three different things: pressure gradient force, the Coriolis effect, and friction. So now we're going to watch a smart figure video on the pressure gradient force, followed by another one on the Coriolis effect, and then I'll explain a little bit about friction and then put all three of those together.
Hello, this is Callan Bentley. Welcome back for another smart figure. This time we're going to take a look at how we represent air pressure on weather maps. We use a graphical device called an isobar. We measure air pressure with a variety of different devices. This is a barograph here that records changes in air pressure over time. Over this section of the continental United States, we might have a bunch of different meteorological stations where we're measuring the air pressure. So let's say this is all data from 10 a.m. on a particular day in millibars. This information is good, but it can be more accessible if we organize it. So basically what I'm going to do here is I'm going to draw on some contours to this data. So basically I'm going to draw a line here around all the values on the map that are less than 990 millibars. And you can see there's only one value on the map that's less than that number. Now I'm going to draw a second contour, and this is basically the 1000 millibar contour, or the 1000 millibar isobar. Isobars basically are lines of equal air pressure. And so everything inside that line is less than 1000. Everything outside that line is more than 1000. Let's go ahead and draw in one for 1010, 1020, and 1030. There's only two values on the map that are greater than 1030. So those are over there on the far right in New England. So we can do two things at this point. Now that we've drawn on these isobars, we can say we've got a low pressure system here over Arizona, and we've got a high pressure system here over New England. And of course, the air is going to want to move from high pressure towards low pressure. So we'd end up seeing arrows on the map that basically represent at least initial wind directions that look something like that. Now the Coriolis effect is going to complicate that, and there are other variables, but that's the basic idea. In order to understand how this relates to wind, you need to understand that the closer the isobars are to one another, the greater the pressure difference, or the greater the pressure gradient. And so you're going to get stronger winds where you have a higher pressure gradient, and weaker winds where there's a weaker pressure gradient. So in terms of the previous picture here, we would expect to see very weak winds over here where the isobars are not closely packed together, and we'd expect to see much stronger winds where they're very closely packed together over here. Okay, this is the figure from your textbook. You can see here that we've got a map of the 48 contiguous United States and adjacent portions of Canada and Mexico. And we have isobars that are drawn on here in a 4 millibar interval. That's in contrast to the 10 millibar interval that I used on my example a few moments ago. You can see here that we obviously have a low pressure area which is centered over southern Lake Michigan, and we've got a high pressure area which is centered over Alberta. The next thing that we can show on this map is how that relates to wind direction. So we've got this key over here that basically shows us the different symbols for winds of different speeds. The little head on each of these symbols basically is showing the direction that the wind is blowing toward. So with the example of this low pressure system here, the air is going to want to move in towards that low pressure area from surrounding high pressure areas. But because of the Coriolis effect, it's going to take on a path that is diverted a little bit to the right of the path it would take on ordinarily. So that's why you can see these things are oriented a little bit right of perpendicular to the isobars. Another thing that I would note is over here you can see there are very gentle wind speeds, basically from completely calm to up around 8 miles per hour. But where the isobars are closely packed together, you can see that there are much larger wind speeds in there that are on the order of 50 or 60 miles an hour. Okay, so what would the isobars look like for this low pressure system here? This is a tropical cyclone, and you can see here that the winds are moving in an inward direction. So what does that indicate about the pressure system, and how would you show that in terms of isobars? Well, obviously, you've got to have a low pressure system here in the middle. So the air is moving in towards that low pressure system. And basically, then it would probably have the isobars very closely packed immediately adjacent to that low pressure zone. And then they would get increasingly spaced apart as you got further out away from it. Thanks very much for your attention. This has been another Smart Figure.
The Coriolis Effect. As a result of the rotation of Earth, the path of any free-moving object will be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is known as the Coriolis Effect or Coriolis force. We first look at the path of an airplane traveling from the North Pole toward the equator. Notice that the path of the airplane on a non-rotating Earth is a straight line from north to south. Notice that once the airplane begins to move away from the North Pole, it continues to move toward its original target at the equator. However, because Earth is rotating, the path traced out by the airplane exhibits a deflection to the right. The rotation of Earth has caused this deflection. The deflection of the Coriolis effect occurs regardless of the direction of movement. Next, we look at the path of an airplane flying west to east from San Francisco to New York City. Notice that the path of the airplane on a non-rotating Earth is a straight line from west to east. Notice that once the airplane begins to move away from San Francisco, its path is deflected to the right by the Coriolis effect. The amount of deflection from the Coriolis effect varies by latitude. The deflection is greatest at the poles and diminishes toward the equator. At the equator, there is no Coriolis effect deflection. In addition, rapidly moving objects are deflected more than slowly moving objects. The Coriolis effect influences many patterns in physical geography. For example, major ocean currents exhibit deflection to the right in the northern hemisphere and to the left in the southern hemisphere.
So as you saw there in those smart figure videos, we can have, a weak pressure gradient force with weak winds, or we can have a strong pressure gradient force with strong winds. And again, the goal here is to try to equalize this pressure. We also looked at the Coriolis effect, and we saw how there's a deflection because Earth rotates. So with the Coriolis effect, the deflection is always directed at right angles to the direction of airflow. It affects direction, not speed. So the Coriolis effect will only affect the direction the wind's blowing, not the speed. It's going to be affected by wind speed. Like she mentioned, the speed at which objects are traveling. So faster, the stronger the wind speed, the greater the deflection. And then the Coriolis effect is going to be strongest at the poles and then weakens as we move towards the equator, where you heard there is no deflection at the equator. So that's the Coriolis effect. So when we look at friction, this is going to be the third effect on wind. It is important only within a few kilometers of Earth's surface. So friction creates drag. So this is going to slow down the air movement and also alter wind direction. So in the upper atmosphere, okay? They are not going to be influenced by pressure, because we have a layer that's called, the friction layer, and above that, the pressure gradient force and the Coriolis effect are working together to direct the flow of air. Eventually, we get to a point where wind is going to blow parallel to the isobars, because we've leveled out the playing field. Essentially, we've been able to more so equalize the pressure. And so these are called geostropic winds. The lack of friction with Earth's surface allows those geostropic winds to travel at higher speeds than surface winds. And so in figure 18.10, well, I don't have that one up here. Figure 18.10, which is on page 557 in your textbook, you can see that these upper level winds blow, at 50 to 100 miles per hour. The most prominent feature of those upper level winds is the jet stream. And this was discovered back in World War II with our high-flying bombers. They are very fast-moving rivers of air, and that's why they were given the name jet streams. They travel between 75 and 150 miles per hour, always in a west to east direction. Okay. And so the jet stream, we know, is what helps to pull weather systems along. These jet streams help to bring, cold weather down. We can get like a polar jet stream. That's what happened back in February when we got those really cold temperatures and the snow. That was influenced by the jet stream picking up very, very cold air in the polar regions and then bringing it south. So in the upper levels of the atmosphere, okay, the Coriolis effect and the pressure gradient forces are going to be at work. There's not going to be any friction. But below 600 meters, we get friction. Okay, it's going to complicate the airflow. So here we are in the upper level wind where there's no friction. Okay, so the pressure gradient force and the Coriolis effect kind of have equal and opposite effects here, and wind is going to blow, in a straight direction, in a right angle. But when we look at winds at the surface, because friction is going to lower the wind speed, it reduces the Coriolis effect. Remember, the Coriolis effect is going to be affected by wind speed. The stronger the wind, the greater the deflection. So since friction is slowing down the wind, okay, then it's going to reduce the Coriolis effect. But the pressure gradient force is not affected by wind speed. So it's still going to be in full effect here. But what happens is that friction and the Coriolis effect kind of have opposite effects here. And so the wind is not going to go at a right angle anymore like it did up here in the upper levels. It's going to deflect toward the pressure gradient force. So it's going to move at an angle across the isobars toward the area of lower pressure. And that's what we've got here. So these little lines would be like our isobars. And so instead of moving parallel to the isobars, it's going to go across the isobars toward the area of low pressure. The other factor that we have to consider is the terrain. The rougher the terrain, the more that's going to deflect that angle of airflow. Over the smooth ocean surface, friction's low, so the deflection is low, the angle is going to be small. But over rugged terrain where there's a lot more friction, the angle that air makes as it goes across these isobars can be as much as 45 degrees. So friction is only going to affect our surface winds, not the upper level winds. So now we're going to look at these areas of high pressures and low pressures that we've kind of been talking about a little bit. So when we look at a weather map, and you'll do this in your assignment, we're going to look at the high pressure systems and low pressure systems. So low pressure systems are referred to as cyclones. And then high pressure centers are referred to as anti-cyclones. The pressure decreases from the outer isobars toward the center in a cyclone, and then in an anti-cyclone, the values of the isobars increase from the outside toward the center. Okay, and so that's what we've got here. So as we go into a cyclone, a low pressure system, the pressure decreases as we move inward. So you see here's the 1,000, 996, 992. But then when we look at a high pressure, an anti-cyclone, the values of the isobars increase from the outside toward the center. Okay. So now we're going to watch another smart figure video about the winds here and the direction of the winds and what keeps low pressure systems and high pressure systems in play and how they, and then we'll get into how they help control the weather.
Cyclones. A center of low atmospheric pressure is known as a cyclone. Notice that air near the surface converges into the low in a counterclockwise direction. The cyclone shown is in the northern hemisphere. As air spirals upward in the cyclone, the wind flow becomes increasingly geostrophic. After ascending, the air diverges into the overall geostrophic upper atmosphere flow.
So we've got our land surface here in our upper atmosphere shown here. So we've got a low pressure system here, okay? This, in a surface low pressure system like we have here, air is spiraling inward, okay? So air is being drawn into the low pressure system. This net inward movement causes convergence. So you can see down here, we've got this tiny little area, okay? And so it causes convergence. When that air starts to converge horizontally, it piles up, it gets taller and taller, okay? And so you get this heavier air column. So this low pressure system is going to cause a net accumulation of air because it's going to continue to bring air into the middle of this little cyclone here. As it gets more air, it increases its pressure. So in theory, the low pressure system would just burn itself out because as it brings more and more air, the air pressure rises, it wouldn't be considered a low pressure system anymore. But that's not what happens. Why? Well, because as that column of air continues to rise, it reaches the upper atmosphere and starts to diverge. Okay. In other words, it starts to spread out. Divergence aloft, so in the upper atmosphere, may exceed surface convergence. So in other words, the spreading out up here in the upper atmosphere can exceed the collection of air here, the convergence of air down on the surface. So divergence aloft and continued divergence aloft means that we can get more and more convergence, more and more air being brought in and spiraling here at the surface, so it can intensify storm centers and maintain them. Inadequate divergence permits the surface low to fill up and weakens the cyclone. Surface convergence surface convergence around the cyclone causes a net upward movement. Rising air results in cloud formation and precipitation, and so a low pressure center is generally referred to as unstable conditions. Sometimes it's not even the surface convergence itself that creates and sustains the low. It's the divergence that's happening up here in the upper atmosphere. Spreading out, or divergence aloft, initiates upflow. So it allows the flow to continue coming in. Outflow near the surface, inflow near the surface is going to be encouraged because now it's pulling so much of that air upward.
As air rises, it undergoes adiabatic cooling, which may lead to cloud formation. For this reason, cyclones are generally associated with clouds and often precipitation. Anti-cyclones. A center of high atmospheric pressure is known as an anticyclone. Wind in the geostrophic flow aloft begins to descend toward the surface high in a clockwise direction. The anticyclone shown is in the northern hemisphere. As air spirals down in the anticyclone, the wind flow becomes less geostrophic. After descending, air diverges in a clockwise direction along the surface. As air descends, it undergoes adiabatic warming, which reduces the likelihood of cloud formation.
So in this high pressure system, you've basically got the opposite situation. Outflow that's occurring at the surface is maintained by convergence aloft. The descending air is going to be compressed and warmed, so we don't see cloud formation and precipitation as likely in a high pressure system. So basically we have opposite situations here. With a low pressure system, we've got air coming in at the surface, so we've got converging at the surface. As it rises, we get divergence in the upper atmosphere. And then for high pressure systems, we have the opposite. We have converging in the upper atmosphere, and as that air starts to fall and get closer to the surface, then it spreads out or it diverges at the surface. Here is a figure that is kind of shows you this. This is from page 559 in your book, where you've got in a low those converging surface winds, divergence aloft, and then in a high pressure system, you've got convergence aloft and divergence on the surface. You'll also notice that they go in opposite directions, right? A low pressure system is going to, those winds are going to spin in a counterclockwise direction. And in a high pressure system, those diverging winds are going in a clockwise direction. So if we kind of continue on here, so moving on into the general circulation in the atmosphere, remember that the underlying cause of all of this is the unequal surface heating by the sun. We also know that because of this, in tropical regions, we have more solar radiation, and at the polar regions, we have less solar radiation. And from our discussion about the ocean, we know that ocean currents also contribute to global heat transfer because we have those warm currents and those cold currents. So now we're going to watch another Smart Figure video that looks at how the circulation occurs throughout Earth.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. This time, let's take a look at the global circulation of air in the atmosphere. If you look at an average global circulation map for the month of January, it looks something like this. You'll note that there is this zone along the equator called the Intertropical Convergence Zone, the ITCZ, shown by the purple line here. and that sort of connects up a series of low pressure areas. And then both north and south of that, there's a series of high pressure areas. So here's like a line of high pressure areas south and another line to the north. And then more towards the pole from there, you've got some low pressure areas as well. Doesn't show up as well down in the southern hemisphere. So what's going on with this overall pattern? Why do we see this? Well, we can start off by considering first off a non-rotating Earth, where basically because of the influence of the sun's rays, so let's consider the sun's rays coming in here from the side and warming the planet, you'll notice that they hit more directly at the equator and they hit more obliquely or glancingly towards the poles. As a result, the Earth is heated unequally and it gets hotter at the equator than at the poles. So what you would expect there is that the warm air would rise away from the surface at the equator and that it would sink towards the surface at those cold polar regions. So you'd end up getting these convection cells that develop on the surface of the Earth, and there'd basically be one cell in the northern hemisphere and there'd be a second cell in the southern hemisphere. That's not what we really see though. Because the Earth rotates, we actually end up getting a series of approximately 3 cells in each hemisphere. Let's consider the situation at the equator first. Again, we have warm material rising off the surface at the equator. As more warm air rises beneath it, it gets shoved both north and south of the equator, and then it sinks back towards Earth's surface at around 20 degrees or 30 degrees away from the equator. These cells end up producing trade winds at the surface. So if you think about those arrows, those red arrows there blowing over the surface, they end up basically being deflected a little bit to the right of their path in the northern hemisphere and a little bit left of their path in the southern hemisphere. So they end up taking on these sort of curved approaches like the arrows you see in the middle of the screen. You'll notice that those arrows converge towards the equator. That's that intertropical convergence zone that we mentioned. And overall, these sort of three-dimensional bubbles that you see here are called Hadley cells. These Hadley cells are important cells of circulation that occur in Earth's atmosphere. Now, north and south of the Hadley cells, there's a similar looking arrangement. And there, between the subtropical high and the polar front, you've got another ring-like circulation cell that produces the westerly winds. And again, just look at those arrows that are flowing over the Earth's surface and think of them being deflected a little bit to the right in the northern hemisphere and a little bit to the left in the southern hemisphere, and you'll understand where the westerlies come from. Finally, at the pole itself, you'll find that there is another convection cell, and that convection cell is the polar high. You'll notice that it produces polar easterlies. Okay, so we end up basically with this sort of series of rings of circulating atmosphere over the surface of the Earth, almost like the planet is wearing a series of inner tubes that wrap around it, and these inner tubes are internally rotating over time. So how would that affect precipitation patterns? Well, here's an answer. If you look at the continent of Africa, you'll notice that Africa has a band of moisture that stretches across its midsection, right around 0 degrees of latitude, the equator. And then there are bands of desert that are about 20 degrees north and 20 degrees south of the equator. Basically what's happening here is that the air is being warmed at the equator. It's rising away from the surface of the Earth, so I've chosen to represent that here with these little red symbols. So think of that as air mass moving up towards your perspective as you're looking down on this scene. And then the next step, of course, is for the air to flow away and flow both north and south of the equator. So that's what's happening here. Then it sinks towards the Earth's surface, as shown by these little blue symbols. And that sinking air is going to be really of different character than the rising air. So the rising air would be all saturated with water, it would cause lots of rain, and that's a lot of precipitation right there at the equator. But the sinking air basically has had all the moisture wrung out of it, and so when it sinks, it's quite dry. And so you end up getting these high pressure zones there where you have relatively dry air and big bands of desert. This circulation cell, this Hadley cell, would not be complete until we had the air moving back toward its origin, moving back towards the equator. And again, in the southern hemisphere, that's going to, due to the Coriolis effect, the actual wind path is going to look something like that. In the northern hemisphere, it's going to look something like that instead. Hopefully you got that right. Thanks a lot for your attention. This has been another Smart Figure.
So as you saw from the Smart Figure video, there are several different types of circulation that are influencing wind direction, wind flow, and those influence weather as well. So now we're going to take a look at the local winds. So local winds are small scale winds, not like we just observed with these global circulation patterns and the high pressure systems and low pressure systems, or cyclones and anticyclones. Local winds are very small scale, produced from temperature differences, and there's three types: land and sea breezes, mountain and valley breezes, and Chinook and Santa Ana winds. And we're going to watch a smart figure video that looks at those three types of winds.
Callan Bentley back for another smart figure. This time we're going to take a look at local winds. And after watching this video, you should be able to describe the formation of 4 or 5 different kinds of local wind, explain where they occur and what time of day they occur. So one kind of local wind that you may have experienced is a very pleasant one called a sea breeze. A sea breeze occurs during the day, so the sun is warming up the land. That causes air to rise and ends up taking on a path that looks something like this. You'll notice that this is basically a convection cell, but it's bringing cool air off the surface of the ocean and bringing it over the land. So if you're standing at the beach or something like that, you'll feel this nice cool breeze coming off the water. Very, very pleasant. The opposite of a sea breeze is a land breeze. This occurs at night when the water is the warm one and the land is relatively cool. So warm air rises off of the water and sinks again over the cooler land. And so you end up again getting a convection cell set up, but it's flowing in the opposite direction. So you'll end up having the breeze blowing offshore rather than onshore. One kind of breeze that we get in mountainous regions is called a valley breeze. Valley breezes occur during the day. As air gets warmed up, it rises up the sides of the mountains. As it does that, it brings its moisture content with it, and that will often trigger condensation and cloud formation up on tops of the mountain peaks. If air is rising, elsewhere air is sinking to replace it, and so you end up getting some cool air sinking into the valley. The opposite of a valley breeze is a mountain breeze. This one occurs at night. Cold air sinks and basically rides down the mountain slopes into the valley. At night, the air above the mountain slopes cools rapidly and drains into the warm valley below, and that creates a mountain breeze. One other kind of breeze that's worth knowing about is the Chinook. The Chinook is a kind of wind that occurs in mountainous regions when you end up having an air mass that moves downslope. And as it moves downslope, the air mass expands in volume, and basically it gets warmed up adiabatically. Because it warms up adiabatically, I've shown it very dramatically here with these angry red colors, but it can warm up by a few degrees, and if that few degrees is enough to cross the threshold between freezing and not freezing, it can encourage the melting of a lot of snow in these regions. So Chinooks are very famous as melters of snow. One Chinook-like wind is the Santa Ana winds that occur in Southern California. Basically, if you have a high pressure system that's centered over the desert regions, it can push out some of that hot, arid desert air, which then flows over towards the coast. And that can be a real problem because it can fan wildfires. So we've got these fires that are burning in several locations here, each of them generating lots of smoke, which shows us where the fires are. But basically, these are being fanned by these winds that are coming off the desert interior here and then going out over the sea. So those are the Santa Ana winds.
So now we've looked at what winds are and where they come from. So now we're going to look at how we measure wind. So when we look at wind, we have two basic things that we're going to measure. We have direction and speed. So direction is going to be the first one we're going to look at here. Winds are always labeled by the direction from which they blow or from where they originate. So if we say something is a north wind, that means it's blowing from the north to the south. The most common instrument that's used to determine wind direction is the wind vane, and it points into the wind. So if it's pointing south, then we know that that would be a north wind. Prevailing wind often is going to come from one direction. So if we say something is a prevailing wind, then it is going to consistently blow more often from one direction than any other. Like in the video you watched about those westerlies that dominate the circulation. In the United States, the prevailing wind comes from the west, and so it moves those weather phenomenon from the west towards the east. So here is a wind rose, and these show the percentages of the time that the winds come from the various directions. So in this example, you see here in the northeastern United States, the longest one here is the northwest. Okay, but over in Australia, you see the longest one is from the southeast, and that's a result of those southeast trade winds. And then in the northeastern United States, the majority come from the northwest, but then secondly from the southwest. And so that kind of gives a look at how those westerlies. Okay, so in the United States, the westerlies dominate. In Australia, the southeast trade winds dominate. So speed is typically measured with a cup anemometer. So in this little contraption that we see here, we actually have a wind vane on one side and then this cup anemometer on the other. And so these little three little things you see here are hollow and almost like spoon shaped. And as they catch wind, as the wind blows through, they're going to spin. And the faster they spin, the faster the wind is blowing. Places where the winds are steady and relatively high are good places where we can put, wind energy. So those huge wind turbines. So changes in wind direction associated with the cyclones and anti-cyclones, so those low and high pressure systems, and they'll bring changes in temperature and moisture conditions. I remember my grandmother when I was a kid, she would always say, oh, that wind is blowing up a storm. And so she was just referring to the fact that, wind, as it moves from that high pressure gradient to the low pressure gradient, the strength of the wind was often related to the pressure gradient. And so a lot of times as the wind would start blowing harder, we knew that, a thunderstorm was coming in. So the next section here looks at El Nino, La Nina, and the Southern Oscillation. And you're going to have a little assignment that you're going to do that looks at these different patterns that result from El Nino and La Nina. So El Nino was first recognized by fishermen off the coast of South America, Ecuador and Peru. And what they noticed is that sometimes in January or December and January, the waters of the Eastern Pacific got warmer. So it would be warmer than normal. And so since this appeared around Christmas time, they named it El Nino, or little boy or Christ child. So what happens in El Nino years is with this warmer ocean temperature, it impacts the weather in Ecuador, Peru, Chile, and Australia, which is basically directly across the Pacific Ocean from this area of South America. The countercurrents among the equator are going to accumulate large amounts of warmer than normal water along the west coast of South America. The warm water, along with the low pressure, cause areas of Peru and Chile to receive a lot more rain, and this can lead to flooding. Also, the warm water blocks upwelling. Now, when we were talking in our chapters about the ocean, we talked about upwelling, which is when we got that colder nutrient-filled water that was able to come up to the surface due to these currents. Well, in El Nino years, that warmer water blocks those upwelling currents, and this causes the fish in that area, especially anchovies, to starve. And so the anchovies, which are kind of at the bottom of the food chain, start to die out. And this affects the overall food chain, which really affects fishing in those areas affected by the El Nino warmer currents. There are some climate fluctuations that are associated with El Nino and La Nina. Now, La Nina is the opposite of El Nino. La Nina means little girl. And so it was named the opposite of El Nino because this is when we have colder than average surface temperatures in the Eastern Pacific. And so when this happens, the atmospheric circulation is dominated by the strong trade winds. And so they generate the equatorial current that flows westward, away from South America toward Australia. So now this is associated with flooding that occurs in Australia and Indonesia. Also during La Nina, the cold Peru current is going to encourage upwelling. So this brings a lot more nutrients up to the surface. And so they refer to La Nina as the gift giver, because the added nutrients that are coming up to the surface are really good for the fishing. And so the fishermen are able to do quite well in La Nina years. And so here we can see what happens. So this top picture is El Nino. So we get a counter current, okay, weaker trade winds. And so we get warm water that's being brought, and we get wetter than normal on around South America. And then in La Nina, we've got a stronger Peru current and a stronger equatorial current. The trade winds are blowing toward the Western Pacific. So we get low pressure systems and wetter than normal conditions in Australia, and then the cool water and high pressure systems over in Central and South America. So we can look at these global impacts. So at first, when El Nino and La Nina were kind of discovered, they thought it was more localized to just these areas here along the equator. But now we realize, of course, they're not, and they do have global ramifications. During an El Nino event, winter temperatures are warmer than normal in the north central United States and parts of Canada. Wet winters in the southwestern United States and in Mexico, and then the southeastern United States experiences wetter and cooler conditions. And we also have noticed that in El Nino years, we have a lower than average number of hurricanes in the Atlantic Ocean. Now, La Nina was once thought, well, these are just normal conditions that occur when El Nino isn't going on. But now we realize that that's not really the case. Colder than average surface temperatures in the central and eastern Pacific can trigger a La Nina event. In La Nina, we get cooler and wetter conditions in the northwestern United States, cold winter in the northern plains, and unusually warm in the southwest and southeast. In your book on page 568, there are some maps here showing these climate impacts on El Nino years in the winter and summer, and then La Nina in the winter and summer. And so in your assignment that you're going to do for this chapter, you're going to look at data and determine, are we in an El Nino year or are we in a La Nina year? The other consideration with La Nina is that we have more frequent hurricanes in the Atlantic. The cost of hurricane damage in La Nina years is 20 times that in the El Nino years. So this southern oscillation is the term that we've given to these pressure changes between the eastern and western Pacific Ocean. And these are associated with the time periods that are in between El Nino and La Nina. So each time we have an El Nino that occurs, the barometric pressure drops in the eastern Pacific and rises in the western Pacific. And as it comes back to an end, the pressure differences swing back in the opposite direction, which triggers La Nina. And we can see that on this here, where we've got higher pressure over here on the western Pacific, lower pressure here on the eastern, and then in a La Nina that flip-flops. We've got high pressure over on the eastern Pacific and low pressure on the western Pacific. And so this seesaw pattern is given the term southern oscillation. Now, what is interesting about this is that it provides us with what we call teleconnection, in that we get these temperature changes and these precipitation changes that are occurring really throughout the world based on what's happening in one small section on the planet. So the last thing we're going to look at is the global distribution of precipitation. And here we go. So here is the global distribution of average annual precipitation. This is in your book on page 570. And so we're going to look at what are some of these factors. Well, it's kind of complex if we look at this pattern. Regions influenced by high pressure with subsidence and diverging winds experience relatively dry conditions, and regions under the influence of low pressure and converging winds receive ample precipitation. So you can look around the equator, those tropical regions that are dominated by those equatorial low pressures are where we find rainforests. So we've got, here in South America, Central America, Africa, over in Indonesia over here. So these are the areas right around the equator that are going to receive the most precipitation because they're dominated by those equatorial lows. The areas that are dominated by subtropical high pressures receive much smaller amounts of precipitation and lead to these subtropical deserts. So that's what we see here in the Saharan desert here. We've got the deserts in Saudi Arabia, the Gobi deserts, the Siberian desert, Atacama. We've got the deserts out in southwestern United States. But that's not the only factor, because if that was really the only factor, then we wouldn't see these areas here away from the equator that are such, dark colors here, indicating that they receive precipitation. So some other factors that influence precipitation is looking at cold air versus warm air. We know that colder air has a lower capacity for moisture compared with warmer air. We saw that when we were looking at humidity in the previous chapter. Low latitudes receive the greatest amounts of precipitation, high latitudes receiving the smallest amounts of precipitation. And so that's why, if we look at how Antarctica and the polar regions up here, they are essentially considered deserts because they do not receive as much precipitation because the air masses are so cold. We also have to look at the distribution of land. Large land masses that are in the middle latitudes commonly experience decreased precipitation towards their interiors. And so that's what we kind of see in North America and in Asia and Europe. We also know that mountain barriers alter precipitation. Windward mountain slopes receive abundant precipitation, leeward slopes don't. And that, again, also looking at In the southwest, we've got the Rocky Mountains here that are going to affect precipitation. Same thing here with the Himalayas. We're going to receive more precipitation on the windward slope of the Himalayas than we do the leeward slope. And then we also have to consider some of these coastal regions that we see here. And we talked about how, we get cooling that occurs over the ocean, and that can lead to some precipitation that results when those cooler air masses and the warmer air masses over land are going to meet. So as a bonus for watching this lecture video, I would like for you to tell me the average annual precipitation for our location, so for D. Queen, Arkansas, as well as the average annual precipitation for Madagascar. So if you'll email that to me, you'll be able to receive some bonus points. So that brings us to the end of our chapter on air pressure and wind. We'll continue in the next lecture with chapter 19, where we really kind of put everything together that we've learned in the past few chapters and discuss weather patterns.